那个都要重开机。还好你注意，我都疏忽掉，真好，因为你帮忙真好。Okay, time is up. 10 after 9. Okay. Again, thank you everybody for showing up, and thank you very much for showing up on time. Okay, especially the weather, considering the weather condition. The temperature, I wouldn't say it's freezing cold, but it is indeed getting colder. And waking up in a cold morning can be very, very difficult, especially for young persons like you, okay? So I really appreciate your participation. Okay, I'm really grateful. And this, what I just said, comes from the bottom of my heart, all right? Learning can be painful, okay? Learning can be painful, but if we really dedicate ourselves into the learning process, I truly believe, and this is based on my personal experiences. Most of the time, I wouldn't say always, but most of the time, it will pay off. Okay? All right. One thing we need to talk about is the remaining schedule of this course, okay? Including the coming exams. According to the original schedule, we're supposed to have the second midterm today. But as you all know, we have a typhoon break last week. So we announced in our Facebook group that the second midterm will be delayed by a week. But I want to discuss another alternative, okay? Next lecture, all right? Not now, because some people are late. Let's wait for them. All right, the first issue we want to talk about today, again, go back to Fourier transform. The subtitle here is energy distribution of the spectrum. So as implied by the subtitle, Fourier transforms tell us or give us valuable information about the energy content of our signal. Okay, now to discuss signal, the first thing we need to do is to define the signal. I'm sorry, if we want to talk about energy, the first thing we need to do here is we need to define what energy is for a signal. All right, here we are talking about signal energy. Why do I have to emphasize that? Because as an engineering student, when we say energy, typically we think about physical energy, like kinetic energy, like mechanical energy, like potential energy, right? Okay, electrical energy, all right? So if we are considering energy, then there are some, if we are considering physical energy, then there are some physical laws that need to be satisfied. For example, conservation of energy, okay? But let me emphasize, this is not the case for signal energy, all right? Signal energy is different from physical energy. By definition, if you have a signal, f of t, its energy is defined as this, all right? You take the square of that signal, and then you integrate from time equals to infinity all the way up to time equals, time equal to minus infinity to time equal to positive infinity. That is, you integrate it from the very beginning to the very end. All right. So no matter how ft lasts, no matter what is the duration time of ft, it really doesn't matter, because this range of integration covers all. Okay. Remember, this is the definition of signal energy. Okay. Why is it different from physical energy? Because a signal can be many things. It can, of course, be displacement, acceleration, velocity, current, voltage, stress, strain, temperature, you name it, right? But FT can also be things like cash flow, information flow, okay? The amount of pollution, okay? The price of a, for example, mobile phone, all right? So how do you define the physical energy of a, let's say, cash flow? There is no clear definition, all right? So that is the reason why signal energy is not the same as physical energy. However, this is the definition for signal energy. Keep that in mind. Now, once we know what energy is, the second thing we need to do is what is the power of an energy, all right? The power of energy is defined by this second equality, okay? By definition, power, from your previous experience, power pretty much represents the average energy per unit time, all right? Now, since the signal varies with time, we can, the power can also vary with times. Depends on what, where you integrate the square of your signal, all right? But from this equality, okay, this is the energy, okay, in the time interval from minus t/2 to t/2, right? And then since the time, the length of this time period is t, and since we are considering the average energy per unit time, we need to divide this term by t, okay? But if we stretch the t to infinity, then what we have is the power of that signal. Okay. These two equations, pretty much, you can consider them definitions. Now, here comes an important mathematical theorems. Definition is something we specify, okay? Because it is something we specify, we don't have to prove the definition. My name is Chen Wenyan, and it is given by my parents, and we don't need to prove that, okay? Because it is just what it is. But if it is a series, then it has to be mathematical proven, all right? Now, what does Parseval series tell us, okay? Remember from the last page, last slide, we know that for a given signal f of t, the power is defined by this equality. Now, we assume f to be a periodical signal, all right? So it can always have its Fourier series representation. Remember, there are three types of Fourier series representations: trigonometric Fourier series, or this compact Fourier series, and exponential Fourier series, right? Now, based on this very definition, f of t, once it is represented, once we have its Fourier series representation, then its power is equal to this, okay? You can compute its power from this equation, all right? Now, what does this tell us? Now, if you look at the form, the structure of the Fourier series representation, we all know that it consists of many harmonic components. each harmonic component is made of a sinusoidal function. And each component essentially has three parameters. The first is the weighting coefficients, which we call amplitude spectrums. This name is given in the context of signal processing and automatic control. The second parameter is, of course, the frequency. And then the third parameter is the phase. So three parameters for each harmonic: amplitude spectrum, frequency, and then phase spectrum. Now, when it comes to energy, when it comes to the powers, only weighting coefficients, these four Fourier coefficients matters. So the power is determined, oh, I should put it in this way. So the power is determined by the amplitude spectrum and is only related to amplitude spectrum. Okay, phase spectrums does not have any impact with the energy of that signal, all right? And frequency also doesn't matter, okay? Frequency has no bearing with the energy. Only the amplitude spectrums has everything to do with the energy. Now, what does Parseval series tell us? Parseval series tell us that the energy of the signal is the same whether it is calculated in the time domain. Okay, when we use this equation to determine the power, we pretty much we essentially what we do is we determine the energy in time domain. However, if we use this second equality to compute the power, we determine the energy from frequency domain. Now, since that we are talking about the energy of the same signal, of the same signal, so these two have to be the same. The result, this equality and this equality, they should get the same results, and that is exactly the case, okay? Because Parseval tell us he knows how to prove it, all right? So let me give you a very simple example to illustrate Parseval theorems. Ft is a signal which is made of two sinusoidal signals, or I should say, which is a combination, represent a linear combination of two sinusoidal signals, okay? Now, of course, these two sinusoidal signals has different frequency and different phase, and they also have different coefficients, all right? Now, based on this definition, okay, let's compute the power of Ft from time domain, all right? So that's exactly what we are going to do, because the definition starting from here, okay, we take the square of Ft, and let's see what happened. We all know that the square of A plus B is A squared plus B squared plus 2AB, right? Okay, so we use that equality. This is, let's say, is X squared. This is, let's say, B squared. And this is, of course, A times B. And it can be shown that this goes to zero due to the orthogonality property of sinusoidal signals. Okay, I did not mention about this orthogonality property, but you can check it out yourself from your engineering mathematical textbook. And this, if you check your calculus table, it gives you this. And this term, this integral will give you this, all right? And this is exactly what we have. from Parseval theorems. Okay, so again, when it comes to energy, only Fourier coefficients or only amplitude spectrum matters. Only amplitude spectrum matters. That is also one of the reasons why, generally speaking, and we pay more attention to amplitude spectrum than to phase spectrum. All right, okay. Remember this example, okay? This is the amplitude spectrum of a signal we saw before. What was that signal? It was this, e to minus t over 2. And then we take a segment of that signal, and that segment is given in this interval. That is, this interval from 0 to pi, okay? And then we periodicalize this signal so we can have its Fourier series representation, okay? We saw this before, okay? And this is how its Fourier coefficients, Cn, changes with frequency. One important property of the spectrum, amplitude spectrum, or the spectra of periodic signal is periodic signals has discrete spectra, all right? Those spectra are discrete numbers, okay? Because they can be expressed as sum of harmonics at integer multiple of the fundamental frequency. It only has energy component at the integer at the frequencies who are the integer multiples of the fundamental frequency. Okay, so if the fundamental frequency, let's say, is 1, then you have frequency components at 2 and 3 and 5 and so on and so forth. But for frequency at, let's say, 1.5, or for frequency, let's say, pi, there is no energy component located at those frequencies because those frequencies are not integer multiples of the fundamental frequency. All right? So remember this, periodical signals have discrete spectrum. How do I know that? Fourier series told me that, okay? Because if you look at its frequency components, its frequency components only occurred at omega 0. Only occurs at n omega 0. Again, this is what we call the integer multiples of the fundamental frequency. All right? Now, by contrast, if we are considering non-periodic signals, then the spectrum is no longer discrete, because if we want to know a spectrum of a signal, what we need is not Fourier series representation. Why? Because Fourier series representation is only good for periodical signals. Unless you want to take a segment of that signal and then make that segment and repeat itself again, okay? Unless you do that. Otherwise, non-periodic signals cannot be represented by Fourier series, okay? However, if you want to understand the frequency components of non-periodic signals, what you need to do is you take the Fourier transform of that signal, okay? The Fourier transform of signal essentially represent the represent the spectrum of that signal, all right? Let's say this is the signal of interest, which is the product of an exponential signal and unit step function. Therefore, since it multiplies due to the appearance of the unit step function, it is by definition a causal signal, all right? Because it has no value. Okay, the value, its value is 0 when t is less than 0, okay? And this is, if you take the Fourier transform of this signal, this is what you're going to get, all right? And then if you take its amplitude, okay, which is this, okay, then what you have is this. This is amplitude spectrum. And if you look at this term actually represents what? The phase spectrum of this signal, all right? And in this figure, it is represented by this dotted curve, all right? So solid curve is the amplitude spectrum, okay, which is this, okay? Apparently, it's a frequency of omega. And apparently, as omega increases, the amplitude spectrum, the magnitude of the amplitude spectrum decreases, right? And amplitude spectrum is always an even function of frequency, all right? Now, for phase spectrum, this is what we have for this signal, all right? Again, it is a function of omega. And it is, when it comes to phase spectrum, it is always a function of frequency, okay? We talked about this before. This is just to hopefully refresh your memory, all right? But one important thing is that these two spectrums have different patterns, okay? Here, for periodic signals, we have discrete spectrums, which means its energy component only exists as the integer multiples of the fundamental frequency. However, for non-periodic signals, what we have is continuous spectrum, all right? That is, you have energy component, not just as the integer multiple of the fundamental frequency. As a matter of fact, for non-periodic signal, there isn't such a thing called fundamental frequency, okay? Fundamental frequency is only defined for periodic signals, right? Isn't that the case, okay? Now, so for every value of omega, all right, you have an energy component. Now, for these periodic signals, we all know that the energy component is represented by what? By this, or as shown by this equality. Is the energy is actually the square of the amplitude spectrum, okay? So Cn squared represents the energy components, okay, of n omega, all right? So if that is the case, okay, what does f omega, what is the magnitude of f omega means, all right? It cannot be energy, okay? It is what we call, I'm sorry, I missed one word. There's one more. This is what we call versus spectrum energy density, okay? Now, to help us understand the difference between spectral energy and the spectral energy density, let's go back to statistics, okay? Now, in signal processing and automatic control, we consider signals. For statistics, we consider random variable, okay? Signals can be classified into periodic and non-periodic signals. random variable can be classified into discrete and continuous random variable. Okay, what is a discrete random variable? A discrete random variable means the value of that random variable, no matter how many possibilities, the possible values are the number of possible values are always finite. Okay, now this, however, is not the case. Okay, for continuous random variable. For continuous random variable, its value typically is a real number. And for a real number, you have infinite possible of values, all right? Because you can have a value which is 1/3. Okay, you can have value such as 1/7. And when it comes to 1/3, what you have is 0.03333 all the way up to infinity, all right? So let's look at a simple example of random variable, okay? Now, the random variable here is the sum of the number of these two dice, okay? One white dice, one black dice, okay? What we care, our random number is the sum of these two numbers, okay? Now, there are many, many possibilities. And we here display all the possible combinations, okay? And then we arrange all the combination based on the value of that random variable, okay? If the value of the random variable is 2, that means there is only one possible combination, 1, 1. If, let's say, the value of that random variable is 6, then we have 1, 5, 2, 4, 3, 3, 4, 2, 5, 1, 1, 2, 3, 4, 5, 5 different combinations. Since here we only have one possible combination, and here we have 5 different types of 5 different combinations. So it is more likely for the random variable to have this value than this value, okay? So here we have all different kind of possible combinations, all right? And the number of combination is directly related to or positively correlated with probability, because where does this probability come from? You divide the number of combination of each possible value by the number of total possible combinations, which is 36. Why is 36? Because for the first dice, you have 3 possible values. For the second dice, you also have 6 different possibilities. So if you put them together, we have 36 combinations. And this essentially represents the probability mass function of that random variable, okay? Each number represents a probability associated with a possible outcome of the random variable. Now, however, when it comes to continuous random variable, we no longer have probability mass function. What we have is what we call probability density function. Now, I'm pretty sure you all heard this before. Okay, in Chinese it's called 常态分布, but in English it is what we call normal distribution. Now, the probability density function here, okay, there is one subtle difference between the probability distribution functions of the discrete random variable and the probability distribution function of the continuous random variable. Okay, here for discrete random variable, its probability distribution is referred to as probability mass function. However, for continuous random variable, its probability distribution function is what we call probability density function. All right. Now, one of the probably most well-known PDF or probability density function of continuous random variables is normal distribution, and it is defined by this equality. All right, fx is a PDF, and this PDF or this probability density function has two parameters. One is what we call mean, all right, which means the average value of the random variable, and the other is standard deviation. Okay, since we are not talking about, since the subject of this course is not about statistics, so I have to ask you to check out the definition of statistics and mu, which is the mean, by yourself. But I'm pretty sure you learned that before, probably in your senior high school, okay? But nevertheless, okay, this is what the what a probability density function of a random variable with a normal distributions look like, okay? Depends on the value of mu and sigma. It look like this. So what do we have here? Basically, it has a Bayer shape, okay? And then the second important property of a normal distribution is that of the PDF of a normal distribution is it is symmetrical, all right? And it only has a single peak. And the peak occurs always at mute, which is the expected value of that random variable. And it is always symmetrical, all right? So if we want to talk about probability for a continuous random variable, what we have is we don't just determine the value of that PDF and say this is the probability. This is the possibility, the likelihood that the random variable will occur, will have such a value. That is not the case, all right? Take this graph as an example. Let's think of X, okay, as the arrival time of a bus, which we are waiting for. Now, essentially, X is equal to X1 minus X0. Let's say X0 is the scheduled time that the bus arrive. Okay, let's say the bus supposed to be arrived at the station at, let's say, 10 o'clock sharp, all right? And X1 represents the actual arriving time of that bus. So it is, if it is positive, which means this bus is behind its schedule because it comes in later than its scheduled time. However, it can also be positive, which means the bus arrived at the station earlier than the scheduled time, all right? So one typical question is that, let's say, okay, I need to wait for the bus. One thing is, how long I have to wait, okay? All right, let's say what we are interested is, let's say this range, -5 to +5. I want to know the likelihood, the probability that the time difference between the actual arrival time and the scheduled time is within -5 and +5 minutes. In that case, what you need to do is first define the time interval that you are interested in, and then you perform integration. All right? And the integral, which is this, represent the possibility or the probability that the random variable, the value of the random variable comes between A and B. All right? That is, the value of X has to be larger than A, but smaller than B. All right? So it's the area under the curve that represents the probability of a continuous random variable. Okay? Now, however, what does the value means? Okay, for any given value of X, it means probability density. Density is not, probability density is not probability, not the same thing. Okay, if you want to know, if I want to determine probability, I have to perform integration just like this. Okay, why can a single time point have a probability? Because a single time point is just one point in time. How many points we have in the axis of time? Of course, infinite numbers of points, because geometrically it is a line. And any single time point is only a point, geometrically speaking, in that line. Since we have infinite numbers of points in a line, so any single point consists the probability that the event of interest will occur at that particular point is of course infinitesimally small, which is 0. However, if you are looking at it, it's not just a single point, but a segment of points, okay? Then you have a probability, all right? Now, so probability density still has something to do with probability. What does that mean? Let's say you have 2 points. One is located at here. The other is located at here, all right? Now, the probability density of this point apparently is higher, larger than the probabilities of this point. What does that mean? It means the random value is more likely to happen here, is more likely to appear here than here, okay? So it's, in a sense, it still represents a relative likelihood, but bear in mind, it is not probability. It's a relative likelihood, all right? Okay, now let's switch our attention back to signal. When we look at spectral energy of a periodic signal, it's very similar, like we are studying probability of a discrete random variable, because we only have finite numbers of possibilities here. This is the reason why this random variable is a discrete random variable. Here, for periodical signal, the spectrum is also discrete. So for each of these discrete components, each of them have its energy contribution. Each of them has its own energy, which is proportional to the square of its amplitude spectrum. And in this case, if we employ compact Fourier series representation, it is actually 1/2 the square of the Fourier coefficients. Now, when it comes to non-periodical signals, we no longer have discrete spectrum. So just similar to random variable, here we no longer have energy for any single value of X, all right? The fx of any single random variable refer not to probability, but probability density. Same thing happened here. For any given frequency, the amplitude spectrum represents the spectrum density. All right? So let me put it in written text. Spectral density describes how the energy of a deterministic signal is distributed across frequencies and is defined directly from the Fourier transform. The energy spectrum density is actually given by this. So the first thing you need to do to determine energy spectrum density is you take the Laplace transform of x of t. Once you have f of t, you take the magnitude and then you take the square, okay? So again, energy comes from amplitude spectrum, okay? It has nothing to do with phase spectrum, all right? So what does XF represent? It represents the energy density, not the energy itself. I should take a square here, all right? I'm sorry. Here, we should have a square here. It represents energy density, not the density itself. Now, what does higher energy density means? A higher spectral density at a given frequency indicates that the signal has a more energy concentrated infinitesimally small neighborhood around that frequency compared to frequencies where spectrum density is lower. So if a frequency has higher spectral density, it means frequency is a relatively large amount of energy is concentrated at the neighborhood of that particular frequency value. However, the total energy of the signal is obtained by integrating the spectral density over all frequencies. Okay, you can also determine the spectral energy not for all frequency, not over the all frequency, but over certain frequency band. Let's say I'm interested in the amount of energy of that signal for the frequency interval, let's say 10 to 20 hertz. You can do that because once you have energies, once you have the energy spectrum density, you can always perform integration. And in performing integration, you have the freedom in choosing the lower and upper bounds of your integrals, okay? So that is exactly what we do here, okay? Now, f of omega, let's say here, the signal is f of t, okay? And its Fourier transform is f omega. Since we are interested in energy, we need to look at the amplitude spectrum. And since we are considering energy, we need to take a square. And this is what we have. Okay, again, an even function of omega. And if we are interested in the energy contained in the frequency band from omega 1 to omega 2, then what we can do is this. I perform integration from omega 1 to omega 2. Okay, and the corresponding integrand, of course, is the square of the absolute value of the Fourier transform of that signal. All right? All right, let's look at some examples, okay? Real world examples. This is separate EEG signals on many different channels, all right? And for any given channel, by using bandpass limitering, bandpass filtering, you can filter out its frequency components. For example, let's say alpha band, okay, which is a very important frequency band for brain wave, is defined as the frequency interval between 8 to 12 hertz. A beta band is related to the frequency band or frequency interval from 13 to 25 hertz. And these are the corresponding waveforms associated with these different frequency bands. Why do we want to do that? Because each band tells us about how EEG, how our brain works. Okay, each brain contains different aspects of the brain operations. Okay, that is why we need to measure EEG in hospital, because by visualizing these frequency bands, doctors can have a better idea of how our brains are functioning. All right. Another possibility is heart rate variability. Okay. Everyone has a heart. Okay. And our hearts are beating all the time. And this is an ECG signal. Okay. Now, here, the signal itself is not this waveform, not an ECG. What we are interested in is heart rate variability. That is how our heart rate, okay, a number of heartbeats per minute vary with time. Okay, it's not a fixed numbers. It is actually a random numbers. Okay, but how and you consider, if you consider it as a signal, okay, let's say what we are interested, this peak, according to the terminology of ECG signals, in studying ECG signals, is what we call R peak. Okay, now the interval between these two R peak is what we call R interval. Sometimes we just call it RRI for simplicity. Now, RRI is a signal, okay? For example, for this plot of the ECG signal, this is the first value of RRI. This is the second value of RRI. This is the third value of RRI. So essentially, it's a discretized signal, all right? It's a discrete signal. And since it can be represented as a discretized signal, we can then use Fourier transform to study its frequency components, okay? And that is the main goal of heart rate variability, okay? And we identify, doctors, medical society identify two important frequency bands, the low frequency band and the higher frequency bands, which related to the frequency band of this and this, okay? And the energy of these two frequency bands has everything to do with Pythagoras activities, which is a very important part, which plays a very, very vital role is in our health, in our normal body function. All right. Now, the next thing we want to study is a very important methods for studying real world signals, okay? And this method is what we call short-term Fourier transform. I'm sorry, it should be, I think it's short-time Fourier transform or short-term Fourier transform, okay? Or both, okay? Okay, or we simply call it STFT. Why do we want to use STFT instead of just directly applying Fourier transform to extract the frequency components of a signal, okay? Because short-term Fourier transform is a very good tool for analyzing non-stationary signals. Now, so the first thing we need to do here in understanding how STFT works. That is how short-term Fourier transform work, is we need to know what is a non-stationary signal. All right, okay, 10 o'clock. Let's take a 10-minute break. Now, please come back in time because